Okay, what up? This is the fourth lesson and the last lesson of this week. I know you're excited. I'm up late recording this because I decided to watch Hunger Games with my roommates instead of record this video. But it was worth it. We're learning about today the inverse of an exponential function. So kind of close off what we are learning about inverse functions, and we're going to lead into the focus of next week, which is the inverse of an exponential function. And we'll learn that name today. So the topics that we're going to be covering are determining if an exponential function has an inverse. We kind of touched on that in the last lesson. Because it was 1-to-1, right? And we talked about like which functions have inverses that are also functions and so forth. And then creating tables for exponential functions and an introduction to the logarithm. Okay, so we're first going to review some parent functions that we've already learned. For each of them, we're going to sketch a graph of each parent function and the graph of its inverse. I'm also going to talk about what the domain and range for each of those are. And we're going to ask, and for these problems, the inverse does not have to be a function. So some of these equations are going to be like set equal to y, and some of them are not. And I'll talk about that when that happens. And then we're going to ask you a couple of questions. So, review of parent functions. Like I said, we'll break it down to original graphs and inverse graphs. So the first one that we're going to talk about is the parabola, y equals x squared. So this is the parent graph for parabolas, right? As you know, it looks like this. Then the domain is all reals, and the range is y is greater than or equal to 0. Now, the inverse graph. So remember, x and y switch. So before you solve for y, which you can't do that for all of these problems, the inverse graph is x equals y squared. But if you do solve for y, you actually don't get a function. You get the positive square root and the negative square root, right? You get a sideways parabola. And remember, the domain and range switch for inverse graphs, so the domain is greater than or equal to 0 and the range is all reals. Okay, next parent graph that we're going to talk about is the cubic function, y equals x cubed. As you know, it's this squiggly curve. The domain and range for both of them, domain and range for the original is all reals. And then again, if you just switch in x and y, the equation for the inverse graph is x equals y cubed. This one you can solve for y. So this one, if you solve for y, you get y equals a cube root of x. So that is the inverse, and it is a function, right? So it looks like that, kind of like a sideways squiggly. And because the domain and range for the original function was all reals for both, so is for the inverse. All right. Next one, we're going to do, there's just the classic line, y equals x, right? We know it looks like that through the origin with a slope of 1. The domain and range is all reals. And if you switch x and y, you get the equation x equals y, which really is y equals x anyways. So it turns out the inverse of this graph is the same line. The domain and range is all reals as well. Okay, next parent function, the absolute value function, right? Y equals the absolute value of x, right? It looks like this with like a v at the origin with the slope of 1 and negative 1. The domain is all reals, and the range is y is greater than or equal to 0. When you switch x and y, you get x equals the absolute value of y. And you can't actually solve for y. It's like a piecewise function. It's not just one function. But when you graph it, it looks like a sideways v. So this is why it's blank there, because you can't really solve for y for that one. And remember I said, it says for this problem the inverse does not have to be a function. The inverse is not a function, and that's why you're unable to solve for y. The domain again and range switch, so the domain is x is greater than or equal to 0, and the range is all real numbers. So next function is y equals the square root of x. It looks like this, kind of like a half sideways parabola. And the domain is x is greater than or equal to 0 and y is greater than or equal to 0. And the inverse of y squared equals square root of x is x equals the square root of y. And again, this one's kind of hard to solve for y, because if you solve for y, you get y equals x squared, but really the inverse of this function is not a parabola. It's kind of like an upwards, it's like this. It's like an upwards half parabola. So if you solve for y, you get y equals x squared, but it's only greater than or equal to 0, right? Because the domain must be greater than or equal to 0 and range is greater than or equal to 0. Okay, next parent function that we've gone over is the hyperbola, right? It's y equals 1 over x, right? It looks like this. Remember, those are the branches of the hyperbola. The domain and range for both of them are all reals except for those restrictions, right? Because there's asymptotes. So the domain is all reals except for x cannot be 0. And the range is the same, all reals except for y cannot be 0. And if you flip x and y, you get x equals 1 over y. It turns out if you solve for y, you get the same. So the inverse of this parent hyperbola is actually the same graph. And the domain and range is the same. Okay, last one, the exponential function. So y equals b to the x, right? Right, because the base can really be anything but 1. I just kind of graphed y equals 2 to the x, right? They all sort of look like this. They have that asymptote at the x-axis, and they grow quite fast. The domain for all of them, no matter what the base is all reals, and the range is everything but 0. Okay, and if you switch x and y, you get x equals b to the y. And for now, we do not know how to solve this one for y. We will learn this next week. And like it looks like this. It's just flipped over, like diagonally right over the y equals x. And y equals x and y equals 1 over x. Their inverses are the same as their original graphs. Okay, and do any parent functions have inverse graphs that are not functions? If so, which ones? It's true. Yeah, these two are the ones that do not have functions, right? Sideways parabola doesn't pass a vertical line test, and neither does that sideways v. So their inverses are not functions. Good job. Okay, let's get into this inverse function. So the function y equals b, inverse exponential function. The function y equals b to the x, right, has an inverse function, but you don't know how to write this in y equals form, which I told you that earlier. So since exponential functions are useful for modeling everyday situations, the inverse of an exponential function is also important. So we're just going to use the base 3 as an example. So even though you may not know how to write the equation of the inverse function in y equals form, you already know a lot about it. So we're going to start with making a table for y equals 3 to the x. So we're going to use these x values, -2, -1, 0, 1, 2, and 3. And then we're going to plug in these values to figure out what our output is. So we're going to start off with an easy one, right? If you plug in 1, you get 3 to the 1, and 3 to the 1 is 3. So we have now the point 1, 3. And then 3 to the 0, right? Remember, anything to the 0th power is 1. So 3 to the 0 is 1. So now we have another point, 0, 1. And then 2, we want to do 3 squared. And 3 squared is 9. And then 3, now we have another point, 2, 9. And then 3 is 3 cubed, which is 27. So now we have another point, 327. The negative ones, right? It's basically the reciprocal of the power. So 3 to the -1 is, 1/3. And 3 to the -2 is equal to 1. Okay, and then the graph, if we plot all of these points, and you're going to see in the graph they're dotted, it looks like this, right? There is -2, 1/9, -1, 1/3, 0, 1, 1, 3, and 2, 9, and 3, 27. Okay, so let's make a table for the inverse. So the inverse is x equals 3 to the y. And like I said, we don't know how to solve for y yet, but we can still make a table and graph it. So let's make a table. So the first point in the original was -2, 1, 9. So now we have 1/9, -2. Then -1, 1/3 becomes 1/3, -1. 0, 1 becomes 1, 0. 1, 3 becomes 3, 1. 2, 9 becomes 9, 2. And 27, or 3, 27 becomes 27, 3. And if you graph all of those points, right, you get this shape. And let's ask some questions. So if the input for the inverse function is 81, what's the output? So remember, the input's x, so it's basically 81. Since it's x equals 3 to the y, it's 81 equals 3 to the what, right? So we figure out basically what power of 3 we get 81. So what is it? You got it. It's 4. Good job. Okay, so now we're going to do an introduction to logarithms. Mathematicians first created a puzzle in ancient India in the 2nd century of BCE that makes the puzzle more than 2,100 years old. More recently, about 700 years ago, Muslim mathematicians created the first tables, allowing them to locate answers to this type of puzzle quickly. So, tables similar to them appeared in school math books until recently. So here, we're going to use the clues to determine the missing pieces of these examples that I'm going to show you. So here are the clues. So you got some numbers here. It says log, and then you have a subscript of 2, 8 equals 3, and then log subscript of 5, 25 equals 2, and then log subscript of 3, 27 equals 3, and log subscript of 10, 10,000 equals 4. Like, what does any of this stuff mean, right? Well, I'll tell you. So these these are like the beginning of logarithms. That's what log stands for. Oops. Let me back that up. Oopsies. Okay, well, too late, folks. Anyways, so this is the relationship, really. So I like to do this kind of snail thing. So whatever this base is here if we look at the first one, the base one, this subscript of 2 is called the base. And if you go raise 2 to the 3, you get 8. So 2 to the 3 equals 8, right? The next one, you get 5 squared equals 25. And then 3 cubed is 27. So then you get 10 to the 4th equals 10,000. So those are my little snails. So basically it's saying like, so this one for example, 2 to the what is 16, right? 2 to the what is 16. So what is it? You got it, 4. Alright, next one. So remember, you take log base, you say log base 2 of 32. That's how you say it. So log base 2 of 32 equals what? So that's the same thing as saying 2 to the what is 32. So 2 to the what is 32. You got it, 5. Alright, last one. Log base what of 100 equals 2. So this is basically saying what squared is 100. So what squared is 100? You got it, 10. Okay, folks, that's about it for the lesson today. Let's just summarize what we've learned. So, first topic of the topics today is determining if an exponential function has an inverse. So, exponential functions have an inverse. It's x equals b to the y. The inverse of an exponential function is also a function, but we don't know how to solve for y yet. Like I said, we will get into it. And then creating tables for exponential functions, right? We talked about that. You basically want to make a table for the exponential function and then switch the inputs and outputs. And introduction to the logarithm, right? We did a couple of those problems, and you'll have some more on your homework tonight. It undoes exponential powers. Okay, I hope you enjoyed this video. Thank you. Goodbye.
Okay.